All right, for the next 20 minutes, I need your attention, and that's doing me a solid, because we're talking about solids. That was a pun. Oof, I hate puns. So let's talk about solids and the different types of solids and even the arrangements that they may appear in. Let's do that now. No, now. Well, howdy everybody, howdy. Welcome to the world of solids. Today we're going to talk about solids, and let's first go kind of general and get more specific as we go along. If you take the umbrella of solids, you can separate it into two kinds of solids. There's amorphous, which are arranged pretty randomly and therefore not very studyable. Basically, what's random we can't quite study in great depth, but or you would in other courses. For example, here's some amorphous solids that touch your life. This is what we call in science glass, and this is a jar of cheap spaghetti sauce that's going to become a pickle jar as I make it one. This is probably, I can't say, it doesn't have a label on there how to recycle. It's probably low density polyethylene. Maybe very familiar to you is candle wax. So let's talk about candle wax actually. So what you've got, I want you to think of candle wax or long chain hydrocarbons. And so instead of having long range order, this would be like if you had a big old container of spaghetti noodles, and the way they're arranged is quite random. So you might have a couple long chain molecules line up next to each other and have stronger London forces than another neighboring set of molecules might be a little bit further apart. And so what you're going to find is amorphous solids generally don't have very clearly defined melting points or boiling points. And so what happens, I just hit the camera, is that you're going to find that those things sort of melt over a range, which if you're a glass blower is good. You don't want to heat your glass and then all of a sudden bang, it's liquid, right? So these kind of things have more of a range, whereas crystalline solids are going to be very well defined. And so it's weird, amorphous solids, it's almost like they're kind of a mixture of themselves because they're sort of random. Here's a figure out of the OpenStax text. You see how the crystalline solid has kind of a very much of a long range order, and the amorphous is kind of just sort of thrown in together. And so what is this long range order? These are what we call, in crystalline solids, unit cells. So what you should be able to do is look at a model of a unit cell, and based on what you see, you should be able to sort of judge what it is. So I'm going to take a bunch of things, and then by the way, when the unit cells repeat, that is called a crystal lattice. I've mentioned lattice energy, and you folks are experts in intermolecular forces, and that's one sort of measure of intermolecular forces is lattice energy. So let's take a look at some more figures from the OpenStax text. That is a lattice of repeating unit cells, and because all of the spheres are the same size, I can say that's probably an element, or it could be a metal. It could be if you were to take some crazy low temperature and have a non-metal solidify, but that would be an element, whereas this would be a compound. So that is an ionic solid, and the reason I can tell this, it's hard to tell here, but those purple spheres are a little bit bigger than the green spheres. So you could say, well, that's probably something ionic, and that's probably a cation, the smaller ones, and that's probably the anions. And so you have that going on. If we were to take some lattices of different solids, you could say, well, that must be a compound. That's actually carbon dioxide. But I could say that's a compound because you got a big old sphere connected to two little spheres, and that could be something if it's carbon dioxide because it's linear. And then you could say, well, this might be a molecular element. So this is iodine, this is carbon dioxide. And so what I'd like to do next is dig in to some unit cells. Now we're looking at lattices there. I want to look at 3 unit cells. By the way, there's about 9, but we're going to study the easy ones because we're only going to study this for 2 lessons, maybe 3. And so there are 3 types of unit cells. You might be able to do some Googling and find examples of these, but I particularly don't like the models with balls and sticks. I like these models which are called space-filling models. And so out of the 9 unit cells, 3 of them are cubes. And luckily, a lot of the elements in the periodic table are cubic unit cells. And the thing about a cube is the math is kind of easy. You might not think it's going to be easy in about 10 minutes, but it is. It's much more easy than if it was a hexagon, something like that, or a rhombus or whatever shape. So let's discuss these 3 unit cells, and then we're going to show you an example of how the unit cell type really has a direct impact on the density, and you can actually prove from the density what the radius is of an atom, or you can actually prove from the radius and the density what the type of unit cell is. So this is very relatable to the microscopic stuff we can't see. But to be honest with you, if you threw a bunch of ping pong balls in an aquarium, you would get one of these types because one's way more efficient packing than the other. So let's talk about the one on the left here. And I want to sort of just maybe get a little closer to these. So let's talk about the one that is on the left, and that is simple cubic. So let's take a good hard look at this. And what I want to do is try to show you how many atoms are in that cube. Now you notice that there's fractions of atoms, and they are bisected, sometimes 3 different times. And so what happens here is the number of atoms is kind of easy to see once you've got some experience. Now, if you're not a 3-dimensional person, well, we're all 3-dimensional people, but I mean, if you don't like thinking in 3 dimensions, I gotta tell you, this is like a muscle that you need to exercise and you'll get better. But you see where it says 1/8 of an atom on the corner. So if you could see this atom right here on the corner, it was bisected once, was cut once, cut twice, cut 3 times. And if you cut something in half 3 times, you've got an 1/8, right? Half of a half of a half. So what you've got here is on each corner, 1/8 of an atom. So we got 1/8 atom. Atom. And if you multiply that by the 8 atoms that are on each corner, that is an atom. That's equivalent of 1 atom. Of course, there's 8 atoms that are associated with that unit cell, but if you take the actual volume of the atom that's inside the cell, that is equivalent to 1. Now, why is it only 1? There's 8 in there. Well, it's because this guy is being shared by 8 other unit cells. And if all there are is corner atoms in simple cubic. And I do want to say something real quick. This is a huge waste of space. All right, this is more of a waste of space than building 10. All right, so what you got going on is this is not the way a lot of substances pack together, and we'll talk about that later on. And so if you throw a bunch of ping pong balls in a fish aquarium, they're not going to line up with the apex of each right on top of each other. So you're going to find out that you're probably not surprised that there's only 1 element that makes this type of unit cell. Over to body-centered cubic, same kind of deal. We've got 8 corner atoms. So those are worth an 1/8, but you see there's 1 whole atom encompassed completely in the unit cell. So just like with simple cubic, we've got 1/8 atom times 8 is 1 atom there. And then we've got one body. So we call these corner atoms. And then we call that a body atom. And so you got one atom plus one atom. There are two atoms in a body-centered cubic unit cell. And there always will be. So if you have a problem, which we're going to deal with in just a little bit, and it says, hey, this is a, well, they don't say hey in problems, but you know, they say this is a body-centered cubic unit cell, then you will be able to say, well, that's two atoms. And if it was simple cubic, that'd be one. Body-centered cubic is more prevalent than simple cubic by far. So here is probably one of the most prevalent unit cells called face-centered cubic. So let's pick the low-hanging fruit. There's in every cubic unit cell, there's corner atoms, and that is going to be 1/8 times 8 is one atom. All right. How about these face atoms have been cut in half? 1/2. 1/2. And there's how many faces in a cube? Well, if you are a gambler and you roll the bones, you know that a cube has 6 faces. So that's 1/2 times 6 is 3. Those face atoms make for 3 atoms out of the unit cell. So 1 atom plus 3 is 4 atoms. Equivalent. Once again, that face atom is shared between 2 unit cells. So the number of, you know, the fraction tells you how many unit cells it's being shared with, whether it be, you know, 1/8 or none or 1/2. So to summarize, the cubic unit cells, simple cubic has 1 atom in it. Body-centered cubic has 2 atoms in it. Face-centered cubic has 4 atoms in it. And then you could say, hey, I can make the sweeping generalization that face-centered cubic is always more dense than body-centered cubic, which is always more dense than simple cubic. And you know what the problem with sweeping generalizations is? You're going to be wrong some of the time because we haven't factored in the radius. Notice that face-centered cubic is a bigger unit cell than simple cubic. And we haven't factored in how much the spheres weigh, which is related to its grams per mole. And so what I'm going to do is I'm going to start you out, I'm going to be gentle with you today. I'm going to start out a density problem that you might run into next. Alrighty. I've sheltered you from mathematics thus far, but we're going to have to whip out one. Go grab yourself your scientific calculator. And 2, let's kind of think about this. So this is how we can kind of relate density, which is easy to measure, right? You could take a piece of polonium. Well, polonium is very obscure. And I'm starting out with an obscure one because it's going to be a simple cubic unit cell. So let's say we got this problem. Polonium forms a simple cubic unit cell. Great. What you should be telling yourself right now, you see the word simple cubic unit cell. 1 atom per unit cell. That's going to be important. If the radius, which we have not really talked about in great deal yet, is 167 picometers, a picometer is a 10 to the minus 12th of a meter, calculate the density of polonium in grams per centimeter cubed. All right, folks, so once again, I'm going to reference the diagram of the unit cell, but you know what I'm going to do? I'm going to go ahead and I'm going to draw it face on. So let's make a cube. Well, a cube looking at its face is going to be a square. And then what simple cubic is going to look like is that. Once again, you can just look at that diagram. I have memorized what that looks like, but you could look at the diagram. So, our goal here is to find density. D equals M over V. And the M is going to be the mass of the unit cell. over the volume of the unit cell. And so mass of unit cell, we're basically asking you what's the mass of one atom. Now if that was Gen Chem 1, you'd be able to answer that question. You'd just say, I'm going to take the number in the periodic table, 209 grams per mole. I would have to have looked that up. 209 grams per mole. And I would divide that by Avogadro's number. That would be how many particles is in a mole, and if it was just divide by that. So the mass of this is going to be pretty easy to figure out. That's a radius. That's a radius. So this is 2r is the length. And so the volume is going to be the length cubed. That's why it's called a cube, right? So let's go and sort of translate this into a strategy for how we're going to solve this problem. And I'm not going to solve this problem in its entirety. I'm going to get it started for you, and I'm going to join you next time. So this is going to be basically, that part is going to be 2r cubed. So let's start and figure out the mass first. M. Mass. What I'm going to start with is the 209 grams per mole. 209 grams of polonium is 1 mole. You might recognize this next part. 1 mole is 6.02 times 10 to the 23 atoms. So if we stopped right there, that would be the number of grams per atom. And actually, we could stop right there. But I'm going to do a little bit of housekeeping here, because we're going to do more than just simple cubic. There are 1 atom per 1 unit cell. All right. Why don't we get a number for that? And let's do that just to make sure that your scientific notation skills are still polished. 209 times 1 times 1 divided by 6.02 times 10 to the 23. 3.4, let's call it 472. 3.472 times 10 to the minus 22 grams. Let's work on the volume next. All right, folks. Now, I want to kind of throw my opinion in here next. You don't have to do what I'm doing here, but I know that was in grams, my mass. And I know that my volume has to be in centimeters cubed. And I know I got L. Actually, I don't have L yet. I got R, which is needing to be multiplied by 2 if it's a simple cubic unit cell. And so you could say, hey, L is 167 times 2, 334 picometers. Now, before I do the 2r cubed, I like to convert picometers to centimeters cubed, and then I can proceed that way. Because when you cube 334, it's going to be in picometers cubed, and then converting cubic units to other cubic units is kind of a bit more, there's more chance that you're going to commit an error. So what I'm going to do is I'm going to first convert L, 334 picometers. Okay, back to good old Gen Chem 1 and the SI system, right? And you might not even be familiar with picometers, but it depends on how you like to do it. I like to put my ones down here. So in 1 picometer, there's 10 to the minus 12th of a meter. 1 meter, there's, and I like to put it, I love powers of 10, guys. Because watch what happens is if I don't call that 100 and I call it 10 to the 2, I can then say that is 330, I don't have to touch my calculator. 334 times 10, and now the powers of 10 add to the minus 10. Now here comes the tricky part. Yes, that is in centimeters. And I'm going to be a bit of a scientific notation snob. if I'm going to make this in correct scientific notation, I need to move the decimal point twice, and that's going to be 3.34 times 10 to the, okay, I made something 100 times smaller here, so I need to borrow from the power of 10, or I need to make sure I'm not doing the same thing twice. I made that 100 times smaller. This needs to be 100 times larger, which is 10 to the minus 8. 10 to the minus 8 is 100 times bigger than 10 to the minus 10. So that actually right there, folks, that's V. And you know what? I guess I lied. We're going to finish this problem. D equals M over V. And so this is going to be 3.472 times 10 to the minus 22 grams divided by 3.34 times 10 to the, oh my goodness, I forgot to cube it. I got to cube that. And the way I could tell is that these should be kind of comparable. So I got to take 3.34 times 10 to the minus 8. Now this is where you got to use your calculator. 3.34 times 10 to the minus 8. I got a y to the x button, so I can just say y to the x, 3, y to the x. And then now that would be 3.72. Let's call it 3.7. Let's call that 3.726. 3.726 times 10 to the minus 23 centimeters cubed. Now you got some decisions to make here. You can crank that into your calculator. But the other thing you could do is you can make them both the same power of 10. If I were to make this times 10 to the minus 23, so the 10s to the minus 23s would cancel out, this would then be made 10 times smaller. So this would be like 34.72 times 10 to the minus 23 divided by 3.726 times 10 to the minus 23. And those 10 to the minus 23, boy, it feels good to do that, doesn't it? And then so you really got 34.72 divided by 3.726. 34.72 divided by 3.726. And that would be 9.3183 grams per centimeter cubed. All right, now I know this is sucking all the fun out of it, but the only number we were given in that problem had 3 digits. So I'm going to round that to 3 digits. 9.32 grams per centimeter cubed. Does that sound good? It don't sound bad. It's a metal. Metals usually have a density anywhere between like 2 and 20. And I think if you look up the literature value of polonium's density, that's pretty darn close. Which means that this is a very good way to either prove a unit cell and its structure from the density and the radius. You can measure radius using a technique called crystallography, and you can basically bounce X-rays off of it and find out the distance between the nuclei. But it's a pretty well-tested way to find the radius of an atom. Or you could go and do the density, and you could calculate the radius from the molar mass. So this is a good interrelatable way to mingle density with unit cells, so that we're not just making something up here. It's very something that can be proven. Okay, hey, this is something that usually is like hitting a brick wall for folks. So we got at least 2 more examples coming in the next video. And we're going to try to deal with the other 2 kinds of unit cells. And so, see you then. Get that scientific calculator out and reacquaint yourselves with it. Bye, folks.